In this video, I'm looking at DX Analytics derivative valuation library. Now, when I look at the whole setup, the book comes with these notebooks. I have cloned it on my system. When you look at the library, the name of the library is DX. And what we are going to do in this session is we are going to look at the third class and look at some of the things that it provides. So this when you are having a portfolio of put and call options, you want to find out how it's going to change when something happens, and you want to calculate the option grade based on any kind of set of equation like Black-Scholes or some other model that you are going to use. So this part introduces into the modeling and introduces us into the modeling and valuation of derivative instruments based on a single risk factor. So if one of the factors change, how are the other parts going to change? And it will also show us how to value a portfolio comprised of such elements, because when you have a big portfolio of derivatives, different calls and puts of different strikes, maybe of the same entity, maybe of different entities, how would that change? So let's see what it imports. So it's importing DX, which is this library that we are talking about. That's also the name of the file. It imports PyLab. Uh, and it says that they have made two libraries for single risk valuation for European and American options. Most of the options are that we use, we can exercise anytime. Most of the model that we use here rely on geometrical Brownian motion, and most of them use Black-Scholes equation to price the option. So the geometrical Brownian motion would be used to predict the stock price, um, and Black-Scholes would be used to find out those option Greeks. Okay, we first use constant short rate. That becomes the first input. Let me go to this link. So this is a very simple equation where we are going to look at different aspects. So this the Black-Scholes equations is used. So the thing that we need to model is the underlying price, strike price, volatility, continuous risk-free, if it's giving any dividend, and time to expiration. With these inputs, we can do all our option Greek calculation. So when we scroll down, we first define what is R. So let me try to run this. I run the first line. Now I see what's inside R, and it's a DX object, if you see here. And since I have imported everything, this thing came to me directly from DX. We can go ahead and look at what is inside DX. But this is dx.frame constant rate. If we were to Google this, then we can get more information about this function and how it's being stored. Okay, that's the second thing. Then we use the market environment to get the dates. If you might be aware about the date time format, and we use this AMI, which puts a lot of assumption that we are going to use into its place. And if you see this AMI, it's going to used here. So by environment, we like kind of switch to some default parameters that we are going to use in valuation. And as I told you, the two most simple assumption of the models would be GPM and BS. Then we define the market parameter and the time. Then we add the initial value, the volatility, the final rate. Let's assume we are doing a currency, so it's ticker. As we move ahead, we can change different models for different things. So if something is mean reverting, or if something has shocks, then we can use that. And then we use path, because we are going to project 25,000 paths using Monte Carlo simulation for that environment for GBM. And then when we add the curve, which is the discount rate, I think here, if you see here, we are going to add this rate. There are some assumptions back in behind, because we can have a flat curve, or we can use a different kind of a curve to be more accurate. Now when we need to run the GBM, if you see here, we're going to use this market environment that we defined and a date. So we are on here on the first 2015, and it's like an annual uh, final date for which we are going to put. So let me go ahead and implement that. When we go to the single option, then we add another constant, and we say that the maturity is this and the strike is this. If you observe, we have the final date and we have the maturity date. So the first instrument we value is a European call option written in a single relevant risk factor as embodied by the GPM model. To this end, we add a maturity date to the market environment and the strike price. We never added the strike price when we did it before, so now we have to do that while we run this. To initiate the new valuation MCS European single class, the following information needs to be provided: name of string object, instance of model class, market environment, and payoff of the instrument. Now we have the call option. So the call option calls a function called valuation MCS, and the name, the underlying environment that we are using. We just defined the GBM here, which was again dependent on this environment and the starting date. Then we define the payoff, which would be NP. This is NumPy library we are calling here, and we are taking a maximum of maturity value minus strike price. In this case, the payoff is that of a regular plain vanilla European call option. T is the maturity, ST is the strike value, and ST is the value of the relevant risk factors at that date. K is the strike price. The payoff ST at maturity of such option is given by this. Maturity underscore value represents the value vector, the value vector of the risk factor at maturity. Any other sensible payoff is possible. So then we say that payoff is np dot maximum. This is what we just did, and we are putting this into a string here, if you observe that. Now since this library is run in a very scripting manner, a lot of thing goes as inside as string and not always as number. And then once we want to calculate that, we'll call this object that we just defined, call underscore EUR, and we'll write dot present value to look at the present value. The idea of using dot present value is that we should be in a position to find out the value at different time when the date changes. So we might be allowed to pass a date parameter in the future. When we want to get delta, we'll write dot delta dot vega, and this is how we can calculate like the single risk derivative valuation using the X library. I hope you like this video. Thank you for watching.